Hi, everybody. Today I'd like to do a little overview of our chapter on logarithmic functions and how we use them in econometrics. So we'll start with this video that'll just define what the logarithmic function is and illustrate it in a variety of contexts. And then in the next lecture, we'll show how we use it in econometrics and in particular, how we interpret the coefficients that have a logarithmic specification. So we'll have three specifications, log linear, log, and linear log specifications, and we'll show how to interpret them. But for this video, we'll just define what we mean by the logarithmic function and uh, get you thinking in logs, which isn't obvious, usually intuitive. Um, so the first thing probably to say about log function is that it's a transformation of a variable. So we take a variable x, any variable, and we apply the logarithmic function to it, and it transforms the values of the x variable into something else, into a y. So it's a transformation. And this transformation of this, the logarithmic transformation, basically looks like a curve. So it takes any value of x and turns it into a y variable, but it's a curve that flattens out over time. And let's take a look at that in R. So we can write a little script. We have load tidyverse. Let me make this a little bigger to see. I will, where's our font size? Yeah, there, it's a little better now, I think. So we have our loading tidyverse. Then we could create a vector of x values. So we have a vector x, 6 values. We'll call the log of x. So the function's as simple as the log of x. We'll call that log underscore x. Now we have that. So we have two variables. We'll gather them in a data frame. And now we can use ggplot to plot the dots. Let's make the size equals 3, a little bigger, right? 1, 2, 3. You can see the shape like this. If we do geom we can see the shape a little more clearly. And we'll see the shape even more clearly if instead of just having 1, 2, 3, 4, 6 points, we have 1,000 points. So let's make the x variable. Now we see it's 1,000 points long. We'll compute the log of x. We'll gather them in a data frame, and now we'll draw the ggplots for them. So we'll draw the scatter plot first. And now we see, right, when we have a lot of x variables, that the scatter plot really does look like that curve. We can also do the line that's connecting all these dots, and we see there's our log function approximated, right? So that's what it looks like. Notice that it changes the scale. The x variable goes all the way up to 10,000, but the log variable only goes up to about 10. So it really compresses the scale of the variation. And then it has this nonlinear shape to it. So going back to uh, our table to think about, or sorry, our handout, to think about what the log function does, we need to think about the natural number. E is the natural number, 2.71828 dot dot dot. So irrational number, doesn't have an end, can't be represented as the ratio of two integers, but it's still uh, it's a uh, it's a number, and it's a very useful number. It's used in finance a lot because it's the limit of 1 plus 1 over n raised to the power n as n goes to infinity. So as n goes to infinity, this number approaches 2.718. In fact, why don't we try that and see? So we have 1 plus uh, 1 over n, and that whole thing raised to the power n. And then we'll see what happens when we have different values of n. So if n is equal to 10, what's this number? It's 2.59. If n is equal to 100, what's the number? 2.70. If it's 1,000, what's the number? 2.71. If it's 10,000, 2.718, right? We're getting close, and we're going to just keep getting closer and closer to the natural number e, 2.718. Now we're right to the sixth digit. We're there. So as n gets larger and larger, this expression approaches 2.718. And we can think of this in finances when we're compounding interest rate, and we start compounding continuously, meaning every single little period, we're dividing the year's interest rate into uh, an infinite number of little periods, and then we're compounding the interest over all those little periods. That doesn't mean that we'll have an infinite amount of money at the end of the year. It means in the limit we'll get 2.718 times whatever the interest rate is as our amount. So it's a very useful number in finance. Coming back to our handout, uh, we'll define the natural log of a number x as the power to which e would have to be raised to equal x. So the natural log is the natural log of x is the power to which e would have to be raised to equal x. So the log is the inverse function, or undoes the exponential function. We can think of e to the y at some value x. The log of x is the number y that we would have to raise e to get x. So that's our, sort of way of thinking about, and it sometimes takes you having to say it over and over again, just repeating this over and over again till you better understand it. Now, what's the log of 5? Well, we can go back over to R and calculate the log of 5. Log of 5 is equal to 1.6. So we asserted that that's the number that if we raise e to 1.6094338, we get 5 back, right? To an approximation. This and R sometimes will round things, so it may or may not be exact. Let's take out decimals, right? There we get 4.99996 by doing that, right? So you should play with R, going back and forth between the exponential function, the log function, to see what you have. Now, we could create a series. Let's call it the um, number of rabbits. The number of rabbits changes with time. So we'll say it, and it grows exponentially. So we'll have it grow at a rate of 0.03 times. Uh, let's say they reproduce every month. Um, so this will be our function that tells us how many rabbits we have for a given number of months. And let's make the number of months be a sequence from 1 to 100. So we'll have 100 months. And I think I need to tell it, yeah, maybe that's all I need to do. Let's see. I forget the exact syntax here. So yeah, we have the number of months, the sequence, 1, 2, 3. So now we have the number of rabbits is increasing steadily, exponentially. So let's graph this so we can do just what we did before, gather things together in a data frame. So we'll gather it in a data frame. We'll have month and instead of the log of x, and we'll have the number of rabbits as our other outcome, and then we'll graph the number of rabbits by month, and we can do it as scatter plots or line plots. So I'm just doing that, right? So we'll gather them data frame and we plot them, right? And that's what an exponential function looks like, right? So let's take the log of this function. So we'll take we'll say the log of rabbits, call it the variable, the log of rabbits, and we'll say that that's equal to the log of the number of rabbits. So that's the log of rabbits. Now we can gather a data frame that has both the number of rabbits and the log of rabbits. And then let's see what happens to the log of rabbits over time. So the log of rabbits will now be our y variable. And voila, right? The log transformation turned a nonlinear function by transforming the variable. We turned it into a linear function. So by transforming the number of rabbits into the log of rabbits, our nonlinear relationship was turned into a linear relationship. So we can now estimate this linear relationship. Months as the x variable, log of rabbits is the y variable. We could estimate that as a by ordinary least squares, because now it's a linear relationship, as we can see. So the log function is often useful for turning a nonlinear relationship into a linear relationship, especially relationships that follow the exponential growth pattern. So we'll see it a lot in econometrics. Let's come back to our handout. Uh, and an important characteristic of the log function is that it acts as what we sometimes call a proportionalizer. That is, for small changes, the change in the log of a variable is approximately equal to the proportional change in the variable itself. And remember, a proportional change, if we multiply it by 100, is a percent change. So a change in the log of a variable is equivalent to the proportional change in the variable. And that's equivalent, if we multiply by 100, to the percent change in the variable. And this holds for very small changes, but it's approximately true for somewhat larger changes. So here in the handout, for example, you can go into R and do this. What's the percent change when we go from 1 to 105? That's a 5% change. We could take the log of 105 and the log of 1 and calculate the difference in those two. Go in R and calculate that. We'll get 0.04888, which is very close to 0.05. So that's the log function. Here's some additional properties of the log function. The log of e is 1, because what's the number that we raise e to and we get e back? Well, it's 1. When e is raised to 1, it's 1. The log of 1 is 0, because when we raise a number to the power 0, we get 1 back. That's from the rules of the exponential function, right? So the log of 1 is 0. The log of 0 is undefined. We can't raise e, which is a number, 2.718. There's no power we can raise it to that will give us 0. So the log of 0 is not defined. We also can't take the log of a negative number, because e is a positive number. So there's no power you can raise it to that turns it into a negative number. Remember, when you raise a number to the negative, it's the reciprocal, 1 over the number raised to that power. So it can't ever be turned into a negative number. Then we have, what else do we have? The log of 1 over x can be defined as minus the log of x. The log of a to the x is the log of a product is the sum of the logs. The log of a ratio is the difference in the logs. And log x to the a is a log to the x. So those are some rules of the log function. We'll make another video now showing how we use the log function in econometrics.